So if we look at the topics of today's lecture, it might be a little strange to realize that we have two such different topics, the vector fields and scalar line integrals. So before starting with any of these two topics, I would like to give a general picture of what we're aiming for. And we're going to see that pretty much both of these things are steps toward accomplishing that general picture. So what we would like to do is consider a very strong generalization of the fundamental theorem of calculus. The truth is that we're not going to see that generalization. Instead, we're going to see different special cases of that general form. And let me put it this way. Up to this point, we have studied the theory of differentiation for functions of several variables, the theory of integration, and there's something missing from the general flow that we had in calculus 1 and calculus 2. So in calculus 1 and calculus 2, in calculus of one variable, if I want to put them in one description, we look at the theory of differentiation, the theory of integration, and then we look at the connection between the two, which is established through the fundamental theorem of calculus. Here, we have seen the theory of differentiation, we have seen the theory of integration. Certainly, the integrals that we computed use the fundamental theorem of calculus for one variable in pretty much every step. But we have not seen something, we have not given yet something that would establish a multidimensional analog of the fundamental theorem of calculus. And that's exactly what we want to do. And I talked in the beginning about a far-reaching generalization of the fundamental theorem of calculus. And you will see that even the description of that will be kind of strange. So it's called Stokes formula. And it says the following. I mean, even the objects in this statement are not known, but if M is a compact manifold, let me say with boundary. I mean, if it doesn't have boundary, then so let's suppose that we have a compact manifold with boundary, and omega is a differential form. Then the integral of omega on the boundary is equal to the integral of the differential of omega on the interior of the manifold. It makes no sense to try to explain all the different components of this definition, and we're not going to do it in this course. A very delightful presentation of this can be found in the book by Spivak, A Calculus on Manifolds. And of course, there are many other books that contain this material, but Spivak's book pretty much starts from scratch and in about 100 pages does everything. I should try to tell you here how this connects to the fundamental theorem of calculus. And let me consider a very specific form of the fundamental theorem of calculus. In fact, this is a quite unusual form, but you can easily see that it's derived from what you have already seen. So imagine that you have a function f with a continuous derivative. Then the fundamental theorem of calculus, the Newton-Leibniz formula, could be given as f of b minus f of a is the integral of the derivative in between. And of course, the usual expression that you get for the fundamental theorems of calculus is that if f uppercase derivative is f lowercase, then the integral from a to b of f of x dx is f of b minus f of a. But you can easily rewrite the fundamental theorem of calculus the way that I just showed you here. And of course, this is over an interval. And in order to see how this is in analogy with the formula that I gave you above, you need to, first of all, this notation with a partial m is just the boundary of m. My integral, my manifold, if you like here, my set is this interval. So it's the interval AB, and its boundary is just the points AB. And in order to keep track of the orientation of this boundary, when we take the integral of the function f over this boundary, which consists of two sets, it's just the difference between the values of the function at the endpoints. And if we view the function as a zero form, then its differential, it's n1 form, which is integrated here from a to b. So believe it or not, the very strange formula that you have on the top, I haven't even said what a manifold is or a compact manifold is or what the boundary is, strictly speaking, is. And certainly I didn't say what the differential form is. But all of these objects are in complete analogy to the well-known fundamental theorem of calculus. So now, in some sense, even though this is the last time that you will see the Stokes formula in our course, we're not going to try to demystify it or explain it or do anything with it. Pretty much what is going to happen is we're going to see expressions that are going to be special forms of that formula exactly in the way that the fundamental theorem of calculus is a special case of that formula. And the interesting thing is, exactly because we will move up to 2 or 3 dimensions, all the formulas that we're going to examine are going to be also generalizations of the fundamental theorem of calculus. In other words, by using any of those formulas, one can prove the fundamental theorem of calculus in very easy steps. I will give you just one of these formulas, the celebrated Green's theorem, where if you have a domain on the plane D, and its boundary is denoted by partial of D, then the integral, this is going to be a vector line integral of P plus Q dy over D is equal to Q sub x minus P sub y in the interior. So here you have pretty much a very similar pattern. So you have something that goes on the boundary. Right here, I'm considering this as the integral of something that looks as a differential form, but later we're going to see that we're going to write it as a vector line integral that applies to a vector field. Vector fields and differential forms are not the same kind of object, but in our case, they can be brought into one-to-one correspondence using a method that will not even become explicit in our course, but there is a way to identify them. And on the other hand, on the right-hand side, you have something that involves the partial derivatives of the objects that you have on the left. So the general pattern again emerges. So you have an integral of one dimension lower on the left than you have on the right. The domain of the interval on the left is the boundary of the domain that you have on the right. And the integrand that you have on the right uses the derivatives of the objects that you have on the left, which is exactly what the initial formula was about. So the term that I mentioned here is called vector line integral. A step toward the vector line integral is a scalar line integral. And the object that we're going to integrate is a vector field. So now all of a sudden, you see the two terms that are in today's lecture that are going to be, in some sense, combined in one lecture, exactly because they're elements of the formula that we would like to eventually present. We're not going to present it today, but we're preparing toward that goal. And it will be a pretty long process, and we're going to see all the generalizations of the fundamental theorem of calculus that are actually used directly in physics in order to derive all sorts of laws, for example, in electromagnetic fields and in electricity and so on, like Gauss's law and other interesting consequences. I'm not going to go over the physics of these formulas, but anybody who takes an introduction to these subjects will come across all of these ideas. So in some sense, I haven't done anything yet in terms of the material that I wanted to cover, but I gave this introduction that should be considered valuable and for what is going to happen next. So now let's get to vector fields and scalar line integrals. So a vector field is, simply speaking, a function defined a domain whose outputs are vectors. So a vector field, wrong tool, sorry about this. So a vector field is a function that assigns a vector to each point in its domain of definition. This is a rather loose description, if you like, and there are much better and much more rigorous descriptions, but for our purposes and for this course, we're going to work with two kinds of vector fields in 2 dimensions, and here's what one of these vector fields would look like, and in 3 dimensions, and here's what such a vector field could look like. And of course, by taking advantage of the basis vectors ij or ijk, you can rewrite this as x squared plus y times I plus yj, yj, and this as cosine x times I plus cosine y plus z minus x squared times j plus, I said z here, but I never wrote it, plus x plus y plus z times k. So the way that you can represent a vector field that's not anything like graph of the function. It's just the mere fact that follows from the description. You can just look at a point and the vector that is assigned to that point. Since the functions are continuous, you're going to see some very nice variation of the arrows, a very smooth variation of the arrows. And let me just say that the prototype for the idea of a vector field is force fields. Obviously, we do live in a force field. That would be our gravity field created by our planet. And we can have all sorts of other fields, electromagnetic fields, and so on. So at each point of this field, or of such a field, we have a force that is defined. And one could ask if we have seen any construction so far that would be reminiscent of vector fields. And the truth is that we have seen one, and that's the gradient. So to each function, f, we correspond its gradient. So let's say that f of x, y, let's start with the function of two variables is x squared y, then its gradient as a vector field is going to be 2xy comma x squared. And we have a special terminology. Gradient vector fields are going to play a very important role. And in some cases, the vector field comes before the function. So we have a vector field that is useful to us, and then we realize that it happens to be the gradient of a function. So in order to lose the dependence on the initial function, we call such a vector field conservative vector field. So a vector field of the form gradient of f for a scalar function. I call it scalar because its outputs are numbers, they're scalars. For a scalar function, f is called a conservative vector field. The function f is called a potential for the vector field f, or a potential to the vector field. So as I told you, in some cases, the function is not going to be referenced in advance. We will just have the vector field, and we will have we will actually try to compute what the potential is. So we'll try to see what the potential is going to be. Just, I mean, conservative vector fields, as I said, are very, very important. Our gravity field is a conservative vector field. But in general, they should be considered to be unusual because, you know what, let me just write a vector field in a rather random way. So something like x squared plus y, x plus y cubed. I don't know, I just thought of two polynomials, right? Without thinking too much. So let me actually put some other exponents here. And because with the one that I just wrote without the exponents, actually my point would not be the one that I wanted to make. So if somebody were to tell you that this was conservative, so this is the derivative of a function f with respect to x, and this is the derivative of the same function f with respect to y, you shouldn't believe it that often without checking it for yourself. Because, look, it's not that simple to just come up with two functions randomly, and one of them is the partial derivative with respect to x of one function, and the other is partial derivative with respect to y of the same function. This is actually quite unlikely, because look, here's what happens. I mean, if you take the derivative with respect to y of the first function, and then you take the derivative of the second component with respect to x, Clairaut's theorem tells you that you should get the same thing, right? But how probable do you think that would be if we choose our functions randomly? So if somebody gives you a vector field p comma q, let's say to put it in a more general way, then if it's conservative, then p sub y should be equal to q sub x. That's a very restrictive condition, which in general is not going to hold. So for the specific vector field that I just gave you, p sub y is 2y, and q sub x is 4x cubed. These two functions are certainly not equal to each other, at least on the whole R2. So certainly this vector field that I chose very in a very generic way is not conservative. We're going to come back to this point, and we're going to see that the whole situation becomes rather subtle, and we need to clarify it further. But for the moment being, we will stop here, having in our hands the definition of a conservative vector field. And let's go to the second topic that we wanted to discuss today, the notion of a scalar line integral. So we can have a domain. This could be actually in 2 or 3 dimensions. And a path, you can always think of a path as the trajectory of a vector valued function. So let's call this path S. So we have a function f, which is defined on this domain. And what we do is we can do the following thing, which is very similar to the process of finding Riemann sums. We can actually subdivide this path into very, very small pieces, and then take an output of the function at a randomly chosen point in each of these pieces, and thus create, so allow me to work in 2 dimensions. So I will multiply the value of the function at each of these points with the length of that small portion and take the sum of all these things. And then what do we usually do with Riemann sums? We consider finer and finer partitions. So we actually divide in smaller and smaller pieces. And in the case of the Riemann integral, that tends to the actual value of the integral. This, in this case, this will tend to the integral of scalar line integral of f along the path ds. So along the path s. So we're going to call this the scalar line integral of f So how do we compute this integral? Obviously, we're not going to work with these Riemann sums. The starting point for computing such an integral is to have a parameterization of the path. So let's say that we have a parameterization R from AP as domain of definition. So R defined on AP. Then the formula that we're going to use is that this is going to be the integral from A to B, so the domain of the parameterization of the composite of the function with the parameterization times the speed. And I would like to refer to this as the pullback of f onto the domain of the parameterization. Because if you think about it, you have an interval and you map it into that domain. And that gives you, and then the function is defined and goes to R. So if you take the composite of these two things, then you get the function that we have here. And it's as if you have the function defined on this path. Actually, it's more common for paths to use C rather than S. So let me change all the S's to C. Sorry about this. And you pull the function back from the actual path onto the domain of the parameterization. That's why I'm going to refer this as the pullback of the function. So this is the formula that we're going to be using. And let's start with an example. So let's see, be the line segment from 0, 1 to 2, 2. Compute the scalar line integral x ds along C. Okay, so the first thing that we need is to parameterize the path. Okay, so how do we parameterize a line segment? To do that, we will use the general formula, which I would like to remind you in full generality. So when you go from AB or A1, B1 to C1 to A2, B2, then you can use the formula R of t is equal to 1 minus t times the vectorization of the first point plus t times the vectorization of the second point. And the domain of definition here is from 0 to 1. The domain of definition of the parameterization becomes as important as ever. And what we have here is the following situation. So our integrand is the function f of xy is equal to x, right? Our parameterization, according to what we just said is going to be 1 minus t times 0, 1 plus t times 2, 2. And t is going to be between 0 and 1. And let's work it out a little. So this is going to be 2t and 1 minus t plus 2t, which is 1 plus t. So that's our parameterization. And if we plug it into f, then this will give us f of 2t comma 1 plus t. This means that wherever we see an x, we put 2t. Wherever we see y, we put 1 plus t. So that will give us 2t, right? And then we need one more thing. So we take the derivative of t, meaning the velocity, and that is equal to 2, 1. And we're lucky because usually these computations can become very hairy. And this will give us square root of 5. So now we can put together the integral. And this is going to be the integral from 0 to 1, y 0 and 1, because that was the domain of the parameterization. We have f of r of t, which is 2t. And we have the speed, which is square root of 5 dt. And of course, this is a very simple integration. So the antiderivative is t squared times square root of 5 from 0 to 1, which gives us square root of 5. And that's the computation. A very, very simple integral. Let's do a few more examples to see different parameterizations and different possibilities. So let's look at the following example. Compute the integral of y squared ds along C, where C is the part of the unit circle in the first quadrant. Okay, so let's take a look at the solution of this. Let's draw our path. It's not really needed, but you know, why don't we draw it? And the parameterization for this path, which we're going to need right away, is cosine t comma sine t. And of course, the domain of the parameterization becomes important. So this is from 0 to pi over 2. And we will also need the speed, right? So we have r prime of t is equal to negative sine t comma cosine t. And the length will be square root of sine square of t plus cosine square of t, which is square root of 1, which is 1. Okay. And what is our function? Our integrand is y squared, and f of r of t will be f of cosine t comma sine t, which is equal to, again, there's no explicit occurrence of x, so there's nothing to put there, but there is an occurrence of y, so this becomes sine square of t. So let's put the whole integral together now. So we have integral from 0 to pi over 2 sine square of t times 1 dt. Okay, how do we integrate this? Our double angle formula. So cosine of 2t is going to be equal to cosine square of t minus sine square of t, which is equal to 1 minus 2 sine square of t. And of course, from this it follows that sine square of t is 1 minus cosine of 2t over 2. So this is going to be the integral from 0 to pi over 2 of 1 minus cosine of 2t over 2, which can be thought of as 1/2, and the antiderivative is going to be t minus 1/2 of sine of 2t. And we want to go from 0 to pi over 2. If you plug in pi over 2 into sine of 2t, you get sine of pi, which is 0. If you plug in 0, you get sine of 0, which is 0. So both of them are 0. The only thing that contributes to this integral is the 1/2 t that gives us pi over 4. And that's this scalar line integral. Now, one may ask, what's the significance of the scalar line integral? And I simply think that a simple interpretation that we can give, which is true with most integrals, is the interpretation of the integral as an average. So there are two steps into this. So the first thing is that if you have a path C, notice that if you integrate the function 1 along C, then you're really going to take the integral of some parameterization of the path of the speed, right? And as we know, this is the length of C. This is a general remark. Every time you have an integration theory and you integrate the function 1, what you find is the measure of the domain. In this case, it's the arc length or the length of the path. Now, if you take a function f of xy, let's say, again, I'm sticking to 2 dimensions, even though the whole thing can be done in 3 dimensions. So if you take a function f of xy and you pretty much take the length of C and you multiply it with the scalar line integral along C of f ds, then this can be considered as the average of the function on C, of the function f on C. So in other words, integration can always be considered as an averaging process. I mean, you do have to divide by the length of C, but pretty much the most important component in this formula is the integral of f. So take any integral, divide it by the measure of the domain, and you get the average for the integral. So that's one interpretation. Our next step will be to extend this to vector fields, and we will see that we have much more satisfactory interpretations in that context. So with this, we come to the end of this lecture. Thanks for watching.